a strange feeling. So,
Right.
all right, maybe it's time to get started. Are you ready to go, Doug?
Yep.
All right. Hello, everyone. Welcome to today's IAIFI Colloquium. It is wonderful to have Professor Doug Finkbeiner, a professor of physics and astronomy at Harvard University, giving the colloquium today. He was instrumental in the discovery of Fermi bubbles, giant structures in our galaxy seen with the Fermi Gamma Ray Space Telescope's Large Area Telescope. Some of Doug's existing efforts at the interface of physics and machine learning involve making neural network classifiers more explainable and also robust against adversarial attacks. But today we'll hear about his work on Milky Way dust maps and the non-Gaussian statistics necessary to model them, as well as how these models map onto physical parameters. With that introduction, please join me in welcoming Professor Finkbeiner. There will be a question and answer session at the end, during which you may ask questions in real time. Alternatively, feel free to submit questions at any point during the talk to be answered during the Q&A. So Doug, with that, please take it away, and we look forward to hearing from you. Thanks.
Okay, thanks a lot, Jim. So this title is somewhat self-explanatory, beyond the Gaussian, a higher order correlation statistic for the interstellar medium. But let me take that apart a little bit. So just in general, we would like a way to characterize non-Gaussianity in physical systems. And there are many examples of this in astrophysics and cosmology, and I'll talk about some of them. But before doing that, question one would be, what do we mean by non-Gaussianity? So really question zero is, what do we mean by Gaussianity? And so I want to be clear here exactly what I'm talking about with this. You're all familiar with a Gaussian distribution, of course, that has some mean and some variance sigma squared. And here are three examples in three colors. But that isn't quite what we're talking about. We're talking about the covariance structure of a data set. So imagine you have two parameters, two axes. You have your multivariate Gaussian case. So you just generalize that previous formula, of course, with some vector x, and you'll have some covariance matrix that describes the covariance of two things. So you can, obviously make a correspondence between any such covariance matrix and a Gaussian in n-dimensional space. And this can be done in high-dimension vector spaces too, like every pixel in an image or every wavelength in a spectrum. So you could be talking about Gaussians not in 1 or 2 dimensions, but in 1,000 dimensions or 1,000,000 dimensions. And then things start to get interesting. You can store a lot of information in a 1,000,000-dimensional Gaussian, right? So this concept of a statistical Gaussian process that generates the data that you're looking at, this process might be stationary or non-stationary. In this context, a stationary Gaussian process means it's invariant under something. So if it's a time series, it might be invariant under shifts in time. If it's an image, shifts in location of the image, and so on. So people often do talk about stationary Gaussian processes. They're nice because they can be characterized with far fewer parameters, right? You just talk about a kernel that describes what this covariance is as a function of difference of position or difference of time or difference of whatever. In the case of a spectrum of a star or a galaxy or a quasar or something interesting like that, those can be thought of as generated by a Gaussian process, but it's non-stationary. If oxygen emits at some wavelength and also at some other wavelength, those are correlated for a reason that has nothing to do with the difference in wavelength and something to do with the physics. So both stationary and non-stationary Gaussian processes are of interest to us. Back when I was in grad school, the kind of exciting new thing that had just happened was that Kobe discovered the anisotropy in the cosmic microwave background. And this was thought of as at the time, and really still is, as a stationary Gaussian process. So there's some pixel-to-pixel covariance in this map. And here I'm showing you what it looked like when I was in grad school, and then WMAP almost 20 years ago, and then more recent data from the Planck satellite at much higher resolution and sensitivity. And there are many interesting ground-based experiments doing this, probably by some people in the room, but I'm just showing some kind of full sky satellite experiments. And the idea here is you've got this covariance between different pixels in the map that depends only on the angular distance between the pixels. So that would be a stationary Gaussian process. And so what's nice about that is you can capture that in a statistic like the 2-point correlation function, or related via a Fourier transform, the power spectrum of such a map. And so here we have a power spectrum, temperature fluctuations in microkelvin squared as a function of angular scale. And there's a characteristic shape to this that can be predicted from a cosmological model and measured from data. And this statistic, this plot here, is invariant under rotation, translation, whatever. It's containing the information you want and ignoring the information you don't want. So just to emphasize again, this is not a Gaussian process because the measurement noise in each pixel is Gaussian. That may also be true. It's the spatial covariance structure of the map that's making this a Gaussian process. So because this is true, the power spectrum or any related statistic essentially contains everything you need to know. I put that in quotes because there may be interesting non-Gaussianities at a very low level in this data set. We want to know about that. But to very good approximation, you get the power spectrum, you have everything. That is the playing field on which observation and theory can meet. And so you can have different models of how the universe is. They predict rather different power spectra. You compare to the data, and you rule out most of the models. So there's a very powerful concept, and that's sort of where we were around 20 years ago with the CMB. I mean, in terms of conceptual development, obviously the data keeps getting better, but it was sort of while I was in grad school that people started saying, "Oh yeah, we just measure the power spectrum, and we got everything." So when you have something that's non-Gaussian in this sense, the information of interest is not captured by a power spectrum. So what kinds of systems would those be? Well, there's kind of subtle non-Gaussianity, which would be, almost, most everything is in one category or the other here, right? So you've got the micro background again, and it might depart from Gaussianity because of something about inflation or novel theories of gravity and so on. The large scale structure of the universe, the distribution of the galaxies and dark matter on very large scales, much larger than our galaxy. That kind of thing is, we think at early times, really quite Gaussian. It's just sort of the same random phase fluctuations set down as are driving what we see in the CMB. But then as they grow over time and structure collapses gravitationally, you build up phase coherence between kind of the different modes of the density fluctuations. And so it becomes non-Gaussian in interesting ways. So there's that kind of thing that's somewhat subtle. You have systems that are mostly described by a power spectrum. And then you have things where it's not even close. A lot of hydrodynamic systems or interstellar dust, which I'll show you in a moment. And basically everything else in the universe is kind of strongly non-Gaussian, and taking a power spectrum of it barely scratches the surface of the information that's there. This is just for amusement. You're not expected to read these names, although you can notice Cora Dvorkin here, who I see on Zoom, and maybe other people in the room. This is one of these decadal survey white papers on interesting things to do for the next decade, and it's on primordial non-Gaussianity. So there's just a lot of people interested in these topics and the different ways that you could get non-Gaussianity. So this is not really a physics talk, so I'm not going to go into this, but just to say that there's a lot of interest. Okay, so those are important questions. Lots of people working on them. My group tends to focus on interstellar dust. So for those of you who are physicists or computer scientists and don't think about dust a lot, there's a lot of stuff out there between the stars. Not just interstellar gas, but dust. You can think of it as small particles of silicate type things like grains of sand, or carbonaceous things like bits of graphite from a pencil, or in the small limit of carbonaceous things, polycyclic aromatic hydrocarbons. So think car exhaust. So there's lots of material out there that can absorb light. So here's a dark cloud where the dust is quite dense. Here's another case where the dust is reflecting light from a bright star nearby. So sometimes you see it in reflection. Sometimes you see both reflection and absorption. It can be quite complicated. like it's an interesting computational problem in its own right to figure out how to do radiative transfer for problems like this correctly, because you're kind of doing an integral over a 6-dimensional phase space or something, and you might have billions of volume elements and whatever. It's a little bit intense to do it brute force, so then you have to think of approximations. Anyhow, that's not this talk. So we have this interstellar dust. It's been mapped in exquisite detail in 2 dimensions, just on the, the sphere of the sky. More recently, we've made a lot of progress in mapping it in 3 dimensions by using the brightness and colors of stars. But of course, those maps are much more crude. They depend on the density of stars available to backlight the dust. And it's just always harder to infer things in 3 dimensions than 2. So what do we want to learn here? We want to learn things about the physical processes that are happening that make dust look like it does. And what are the parameters of those processes? So some things would be the density of the material, the magnetic field. So these dust grains actually in general are charged. The photoelectric effect will knock off electrons so they can feel the magnetic field. They also feel the gas, which tends to be tied to the field if it's partially ionized, which it basically always is. At least at the 10 to the minus 4 level, you get cosmic ray ionization. So the gas is never totally neutral. It always fills the magnetic field at some level. So that kind of shapes things. You can calculate the Mach numbers. So relative to the speed of sound, you have a sonic Mach number. Relative to the propagation of alphane waves in a magnetic field, you shake the field and it does this. That gives you speed. So you have an alphanic Mach number relative to that speed. So there are lots of parameters we might try to derive from images like this. Okay, so dust has filaments and clouds and cloud edges and things that are very non-Gaussian structure. There's a lot of phase coherence here. These are just 3 random spots on the sky from the WISE Sky Survey Atlas. So WISE is the name of a satellite launched about 10 years ago. Ned Wright was the PI. Aaron Meisner, former student of mine, and I did a data analysis of it to try to clean up the images and make them as pretty as possible for various uses. And they're all available, that URL. But the point is, you might imagine some of these structures look like maybe they're sort of magnetic dominated. Some of them look like it's just hydrodynamics, like a bit of dye dropped into a cup of water or something like that. They're evocative of different things, but how do you really know? Okay, so we would like a way to characterize such structures that's more than just the power spectrum. We'd like it to be translation invariant, rotational invariant, preferably robust to projection along the line of sight. That's a somewhat subtle thing in the cosmology world with the power spectrum. There's something called the Limber equation that relates the 2D version of it to the 3D version of it. So Corey Francisco Park is a student working with me who's given some thought to how to make that association between the 2D and 3D versions of this. It's good if it's robust to noise, or at least if we understand exactly what noise does to the statistic. We want to understand what change in the point spread function does, or different spectral regimes we look at, or things like that. So you might be sitting there thinking, well, this sounds like a problem that's cut out for a convolutional neural network. Why don't you just go straight to a CNN and be done with it? And there are some examples of problems like this where people have done that. But what we keep coming back to is quantity and quality of training data, right? We only have so much sky. We can only survey it at a certain angular resolution until we spend $1 billion and go build a bigger telescope. And so to some extent, we're really in the data starved limit for a lot of these projects. So that's something to keep in mind, that there isn't just always quite enough data to train a CNN. And so what I've been looking for many years is some sort of middle ground between a CNN and just simple Gaussian statistics that just calculate a power spectrum and call it a day. So we were inspired to learn several years after the paper came out. This is a 2012 paper by Bruna and Malah on invariant scatter and convolution networks. But we're kind of inspired by this work because what they've done is start with a filter set that's predetermined as being some kind of wavelets. It may not matter hugely what the wavelets are. We think it does matter, and so I'll talk about that. But you start with some wavelets, and you generate this translation invariant representation of an image. I'm going to use image generically here and show you 2D things. You can do all of this in 3D if you want. So we have this sort of generic representation that's translation invariant. It can be made to be mostly rotation invariant, stable to deformations, preserves the information that you want for classification. And so this approach kind of cascades wavelet transform convolutions with a nonlinear operation, in this case, the complex modulus, and then average, and then repeat. So again, we're building this out of wavelets. I'm showing you the wavelet from their paper. I'll show you our favorite wavelets later. But this Morley wavelet is kind of a very simple thing. It's just a plane wave, a complex plane wave, e to the ikx, and then it's windowed with some Gaussian. And so here's the real part and the imaginary part of such a wavelet. So you just kind of get 3 bumps or 2 bumps or 2.5 bumps or something in your wave before the Gaussian cuts it off. And in the Fourier domain, it looks like this, where it's concentrated around some wave number. Okay. So you make a bunch of these wavelets, psi jl, and j is the index that reflects the log of the size of the thing. So in a 256 squared image, we might use 6 scales, kind of throw away the biggest and the smallest scales. And then we might have 8 angles in the half plane. Why do I say half plane? We're going to take the FFT of something, we're going to carve it up in the Fourier domain, and then we're going to take the modulus. And as you may know, if you take an image and rotate it around 180 degrees and take the Fourier transform of it, you just pick up a phase factor. You flip the sign of the imaginary part. So when you take the modulus of that, that's invariant under 180 degree rotations. That may be a desirable property when we go in the direction of rotation invariance. It may not actually be a desirable property in some cases, and we can come back to that. But we do have 180 degree symmetry and everything we're talking about. So we're just carving up half of the plane in angles. So that's why I say 8 angles per half plane. Okay, so the recipe is take an input image I, convolve it with each of these, in this case, 48 different wavelets. Take the complex modulus of that, right? Because you get complex numbers out, they're complex wavelets. And then you repeat this usually 2 times. We could go to 3, but you get more and more coefficients the more, the deeper you go. And 2 is usually enough. So the first iteration of this, you have your image I convolved with some wavelets, you take the modulus of that and you average over the image. This is just some normalization factor, don't worry about that. Then at the next level, instead of taking the modulus and averaging, you take the modulus, convolve it by another wavelet, take the modulus of that and average. So you could do this as many times as you want, but at each layer here, we're taking something, we're convolving it with something, outputting the averages, calling those the S1 coefficients, then taking those images, convolving again, outputting those averages, call them S2. So this is just writing it in equations again. And you may stare at this a moment and say, well, come on, this is nothing but the square root of the local band power. So that's easy to understand. You've just taken a chunk of the Fourier transform. And so gathering these together and averaging over angle L, you get something like the power spectrum. But then what do you get at the second order level? You get some nonlinear coupling of various scales and angles. And so that's interesting. All the Gaussian stuff is represented by this first level coefficient S1, but then you get access to the non-Gaussianities at S2. And it's worth pausing for a moment here to comment that there's some similarity to a CNN. So they both involve some notion of take an input image, convolve it with some filters, put it through some nonlinear function. Here it's just a complex modulus instead of a ReLU or something. Output some things from that, then convolve again with each filter and keep going. Unlike a CNN, WST kind of sees or is sensitive to all scales at each step. Right? A CNN tends to be sense of the large scales by doing convolutions with small filters and then cooling down and doing it again, cooling down, doing it again. And after you've cooled down several steps, then the filters are effectively large on the original image, although they're acting on activations from these other filters. Whereas here, we're just doing all scales of wavelets at once. It's the same price. It's all done with Fourier convolution, so it doesn't matter how big the wavelet is. Okay, another difference is a CNN has to learn its filters. I know that might be overstated. What people might do in practice is take their favorite ImageNet winner and take the filters it was trained on, and then only train the later layers of the network. But at least in principle, CNN always has to learn its filters. For WST, the filters are fixed. The nonlinear transforms are fixed. There's not really anything to train here other than you might have to train something on how you use the outputs from this scattering network. But it's the network itself is determined by the geometry of the problem and nothing else. There's no training. And since everything's built on FFTs, it executes really fast and on a GPU blindingly fast. Okay, so just to give a little bit of an example, this is still from the Bruna and Millat paper. Here's something called a Brodot's texture. And if you scramble the phase of it, it looks like this. So to my eye, these look like very different things. If you take the Fourier power spectrum, they look identical. This is some way that Millat likes to package the coefficients. So don't worry exactly about what this representation is, but radius has something to do with radius in this Fourier space, and angle has something to do with angle. And these are the S1 coefficients, and they look the same, just as the power spectrum looks the same. So in the Gaussian limit, these are the same image. But then when you go to the S2 level, these look very different. So that's just to give you some feeling that, okay, this is latching on to something. Okay, so we saw this paper and we said, this is brilliant. We have a statistic here that's fast and easy to compute and hopefully easy to understand. It's translation invariant and somewhat rotation invariant. Requires no learning in the conventional sense. And we can kind of cleanly say S1 is sense of the power spectrum and S2 is sense of the non-Gaussianity. So now what? So, in their paper, they show that this classifies textures very nicely. So if it can do that, can we classify density fields in the interstellar medium in an interesting way? So let's apply this to an image of interstellar dust. On the left, we have just random patch of dust on the sky. On the right, we have the same thing with the phases scrambled. Okay, so those two images have the same power spectrum. And so before I show you the results from this, I have to explain LDA. So this WST thing, it's outputting hundreds or thousands of parameters. We need to do some kind of dimension reduction to get things back down to 1 or 2 or 3 or 10 parameters that we can kind of think about, or else my claims that this is so explainable and easy to understand won't satisfy you. So how do we boil this down to a few useful parameters? When confronted with something like this, the first thing you might say is PCA. PCA is not helpful here. Just as a demonstration of this, and this is from a paper led by Andrew Sagery, physics student at Harvard. So Andrew said, let's just take 4 classes of images here. Images of dust from the Schlegel-Finkbeiner-Davis map from 1998. The same thing with random phase. Then just some random noise in red and smooth random noise. So it has correlations pixel to pixel in orange. And you take the principal components of these things and they all land on each other. That's not interesting because PCA identifies a linear basis that's telling you where most of the variance is. But we don't want most of the variance. What we want is something like linear discriminant analysis, for example. That finds a linear basis that maximizes separations of classes. So it's doing a rather different thing than PCA. It's similar in the sense it's just finding a new linear basis in this high dimension space. Nothing profound here, but it's finding a basis that separates classes. So it's supervised, not unsupervised like PCA. You have to tell LDA what your classes are, but we have 4 different classes of points here. When you do that, they're easily separated. I'm just showing you the first two linear discriminants here. There are more dimensions in the space. So the blue and the green separate perfectly in some other dimension. And what we get then, if we look at this as kind of a true label on this axis and the recovered label on this axis and the test train precision, it's 100%. It's very easy to separate these things. So again, to just say that clearly, SFD and SFD, so dust and dust with the phases scrambled, they're much closer to each other in this space than they are to random noise, but they still separate perfectly. So that tells you that the WST is picking out something about the phase coherence of these thousands of dust images that we're applying it to and saying, oh, these actually look like dust. They don't look like dust with random phase. Okay, so that problem was too easy. Let's try a toy problem that's related to the interstellar medium that's a little bit harder. So here are some simulation slices from a magnetohydrodynamic simulation. There's a whole cottage industry out there of people who do simulations like this and try to learn things about how the interstellar gas and dust interact with all the things that are going on, right? The magnetic field matters, energy injection from supernovae might matter. They're all there's lots of good physics there. And so these simulations can get quite complex. Here we're just using as this example some isothermal, relatively simple simulations where you're just driving turbulence on some scale in a box with periodic boundary conditions and a magnetic field. And you can talk about the Alfvénic Mach numbers and the sonic Mach numbers and so on. And so the question then is, can this wavelet scattering transform plus linear discriminant analysis tell these apart? Can you look at this simulation and say, oh yes, obviously that is sonic Mach number of 2 and Alfvénic Mach number of 0.7? And the answer is yes. This works quite readily. So in this case, WST is outputting vectors in an 1827 dimensional space. We run this on these, we just say these are 8 classes. You can do this as a regression also, but just to kind of think about this in a simple way to start. 8 classes of images, we have thousands of each of these. And those correspond to thousands of dots in this plot in the 8 different colors. And with a 94% precision, we can tell you which blob a given input belongs to. And, the places where it makes mistakes are just, the blobs are slightly overlapping. You could have put the blobs further apart and made this number 100%. So the exact value of this number isn't really the interesting thing. The interesting thing to me is that there's a mapping from the Alfvénic and the sonic Mach numbers of these simulations onto just some very simple 3-dimensional linear space where it appears as kind of a helix. Why should that be? I don't know exactly, but this gave us some hope that there's a there here, right? We're using this very simple transform and we're mapping something that looks kind of complicated onto a simple space. That was, I believe that plot was mixing all of the different magnetic field directions together, but you can say, okay, let's say the magnetic field is always along the X direction of the box. And then we're going to see if we can separate slices orthogonal to the X direction with slices orthogonal to the Y or Z directions. And so this does just what you want. The X direction slices are not like the others. You can't tell Y and Z apart. You shouldn't be able to by symmetry, but the fact that the magnetic field is dominantly in one direction comes through clearly. So that's kind of cool. So with something like this in the toolbox, we might be able to, in the future, we can't literally do this yet, but this is where we're going, to try to just look at maps of dust or gas or whatever in the interstellar medium and just read physical parameters off of them. We might also be able to help use this to constrain inferences about dust in 3 dimensions. I could give a whole hour talk on what my group has done with inferring the distribution of dust in 3 dimensions using the brightnesses and colors of billions of stars. When you do a project like that, you want a prior. And the best thing that's usually done nowadays is a Gaussian process prior. Most people don't even get that sophisticated, but you can use a Gaussian process prior. And Torsten Enslin's group at the Max Planck Institute for Astrophysics in Germany has been a leader in that regard, and we're working with them now on that. But that immediately raises the question: well, the dust is obviously so non-Gaussian. Shouldn't you have a prior on these inferences that takes that into account? So I'm going to get out of full screen mode for just a moment because I'm told this video plays much better. Hopefully it doesn't look too jerky here. This is a video we made years ago, actually. Gregory Green, my former student, made this video of some of the dust near us in the direction of the Taurus and Orion constellations. And the visualization here is just we're moving around the sun as if we're about 100 million times farther away from the sun than we actually are. So you can see the parallax shift of that dust as we move around the sun. And it's just kind of cool to think that you can, we weren't using any emission from the dust to make this map. We're merely using the absorption of the dust and the fact that we have some idea where the stars that the dust is absorbing are and how the dust absorption changes the color and brightness of the stars. So that's the kind of thing I would like a better non-Gaussian prior for, because to take a map that's going to look like this and be so non-Gaussian and have a Gaussian process prior in your inference is a little bit, it works, but okay. So to make a more expressive prior, sorry, this is just saying what I already said. So let me tell you about our current work now. We are driven somewhat by the thought that the stuff we're doing here really should be rotationally invariant. And I used some weasel words before about the WST being kind of rotationally invariant. It turns out if you look in detail, it's more rotation invariant than a lot of things, but it's not really. And so we don't know quite how well we need to do on that front, but we could try to do better and see if it matters. So we have invented a new filter bank that is compact in the Fourier domain. It conserves image energy. So if you sum the squares of all the wavelets, you get 1. It's exactly translation invariant. It's approximately rotation invariant, and the implementation of this is quite fast. And I'll show you some examples on mnist, because why not? But first, we didn't know what to call these things. Everyone has to come up with a name for their wavelets. These are triglets because they're built on cosine functions. So here in the Fourier plane, here are 3 different wavelets, different angles in red, blue, green, and you can kind of see red, blue, green here. This is the radial profile of them. In the radial direction, they're uniform in log R. So there's red, blue, green in the radial direction, and we go out to the Nyquist frequency at the edge of the box and stop there. So that's just giving a sense of what shape these are. We can generate these with different amounts of overlap. If you left the blue one out, then these would be functions that if I sum the square of the green and the red, I get 1. Okay, but we can have a double overlap and we can have things like blue, halfway in between the green and the red. So what do these look like in practice? Here's the Fourier space version of, just for some random j I picked, L equals 0, 1, 2, showing you how they rotate through the angles. Here's the real part and the imaginary part of these wavelets. So they look a little bit different than the Morley wavelets. They're exactly compact in the Fourier domain. They're slightly less compact in the real domain. For the problems we work with, I don't think I care. For other problems, you might. As with all wavelets, you have to be careful about the smallest and the largest scales. So here's the whole filter bank going from small to large. We're changing the scaling of these images accordingly so they look like they're all the same scale. But if you look in closely, let me zoom in on the green box and the yellow box here. You can see that the small wavelets at, say, j equals 1 are quite coarsely sampled in the real domain. You see they're kind of pixelized, and they're big and nice and smooth in the Fourier domain. Of course, at the big end, the opposite thing happens. They're smooth in the real domain, but in the Fourier domain, they get very pixelated. And so we're trying to build something that's rotationally invariant out of these very pixelated things. So that's going to compromise the invariance. There are things we can do to make it less compromised. We can spread the wavelet out over a broader angular scale and then double them up. That works better. It's better sampled in both Fourier space and real space. So then what we're going to do to try to make these isotropic is build what we call isocoefficients. So we take linear combinations of the coefficients that are nearly rotation invariant. So before we had S1 coefficients that are a function of some size scale and some angle, and then S2 that's sort of, some wavelet, take the modulus, convolve with another wavelet on another size J2 and angle L2. So this is going to become just a function of J1, just a function of size, like a power spectrum. And then S2 is going to be a function of the two sizes and the delta angle between the two wavelets we're convolving. So this is a quantity that's rotationally invariant, sorta. So here's a spinning rod test. We generate images of a rod and rotate it around. And as a function of the rotation angle from 0 to 180 degrees here, we're just plotting all of these few hundred isocoefficients that we get in that way. And this axis is image power. So if we define, I didn't say much about this, but you can output the modulus averaged, or you can output the modulus squared averaged. For this plot, we're outputting the square. So that's something like power. You can use Parseval's theorem. You can use lots of fun tricks. But the nice thing is if you do it this way, the sum of all of your wavelet coefficients equals the total power in the image, meaning the total variance of the image, the sum of the squares of the pixel values. So, so that's nice then, because these different coefficients are kind of calibrated relative to each other in terms of image power. And you can see the ones containing most of the power up here are really quite flat as a function of angle. The ones that contain a billionth of the power, they're not flat at all. They're fluctuating all over the place, but maybe you don't care. Okay, another way to look at this is depending on how much we spread out the wavelet in angle, that being this W parameter, we get some amount of image power root mean square as a function of the coefficient mean. And the more we spread out the wavelet, the better we do. At some point, it'll hurt your classification if you do that too much. As a fractional RMS, you see we can drive things down to the few percent level pretty well. If we're willing to, in the lower right panel, what we're doing is we're taking the input and rotating it to a few different locations and then averaging the outputs from those. Those become much more rotationally invariant. You can drive things down to the part in 1,000 level for the coefficients you care about. So how well do you need to do on this? We don't really know. It depends what the application is. But we can force these things to be really quite invariant. For reference, if you do a nice Lanczos interpolation of an image to shift it or rotate it, that introduces noise at about the 10 to the minus 4 level in these things. And so in some sense, the invariance is not defined better than that. And so chasing things at the 10 to the 9 level is not interesting, right? You have to put a floor on what you care about. Okay, so because machine learning talks of any kind have to involve mnist, we just played the game here. That is not what we did this for. It's not what it's optimized for, but we have to try and just see, is WST plus LDA going to take mnist digits and separate them in some low dimension LDA space in a reasonably nice way? And yeah, it works pretty well. 1 is this color, 0 is this color. So you see the first thing that LDA does is it says, ooh, 1s and 0s are a lot different. Okay, now once I've got that out of my system, what's left over in like the second versus third dimension, and you see the different color blobs separate pretty well. It's traditional in situations like this to worry about how similar 6s and 9s are. Remember I said we have 180 degree symmetry in what we're doing. And so it's not surprising that the 6s and 9s are pretty close to each other at all these projections. And we do have some 6 and 9 problem here. That's by far the most common mistake that it's making. Okay, so now let's do the isocoefficients. Remember, that's the same thing, but we're taking linear combinations that should be close to rotation invariant. And then we can feed in mnist digits with random orientations. and we get this. Unsurprisingly, again, the 6 and 9 issue is kind of painful, but otherwise we do a pretty creditable job of separating the different digits. You know, this is not cutting edge in terms of that exact test. People have done, I guess I should explain this table. So nrnr means not rotating the training data and then not rotating the inputs. So if you know the orientation of the thing you're looking at, you get this column. If you just scrabble up all the training data, you know, augment it with all the different rotations, and then test against that with rotated data, you get this column. And so like a typical planar CNN that's not trying to do this will, you know, benefit a lot from that data augmentation, but still not do great. And then this is if your training data is not rotated, but you rotate the inputs. And so, of course, a neural network that's not been equipped for that is going to do a terrible job. You wouldn't expect it not to. But what we're claiming here is our wavelets plus LDA, the ISO version of that, does pretty well. So you can go all the way to spherical CNNs. I put a few references in here. People in just the last year or two have made a lot of progress, or three, have made a lot of progress on this by trying to build neural networks on a sphere that are like, where the invariance is built in. And yes, they do quite well, right? But that's a vastly more complicated thing than what we're doing. And so the question is not, can we beat papers like that? I think the question is sort of in the data-starved limits, how do we do? And so this is another way of kind of looking at accuracy as a function. So blue is train accuracy, red is test accuracy, as a function of the number of training samples per class. And in the mnist case, there's 6,000. But if we use 2,000 or 1,000 or 500, we do almost equally well. Even if we go down to 200, we get a little bit worse. So that's encouraging. Another sort of interesting thing is fraction of false labels. So here, if we have training data that's contaminated with false labels, and this should probably say random, not false, 100% false here means that 10% of them are still correct because we're just randomly choosing 1 of 10 labels. So there's a fraction of random labels. And as you mix in randomness to both the training and the test, this falls linearly, as you would expect, until you get down to right at the end. Train will do better than test because the model has a little bit of capacity to memorize the training data, even though it's garbage, and does better than the test, which just goes to 10%, which is random. However, this test clean line is what intrigues me. So this point up here means half of the training data has random labels. This is garbage data, and yet the performance decreases ever so slightly. So I think that kind of thing is really interesting. You know, try training your neural net with 90% bad data. So to summarize this, because I want to leave time for questions, patterns of non-Gaussianity generally appear in physical systems of interest, and yet we make the Gaussian assumption all over the place. And it's usually because it's convenient and easy and definitely the first thing to try. But as you try to go to the next level of let's keep track of the non-Gaussianity in some way, it can be hard to know what to do. Maybe you want to calculate a 3-point function or something, but then you find it's very time consuming, or you know, whatever. It can be hard to know what to do. You can go all the way to a CNN and get really high sensitivity to such patterns, but that may often require more training data than you have. And so we're looking for this middle ground where we can get at non-Gaussianity, have sort of built-in invariance under translation and rotation, and maybe possibly exceed CNN performance when you're in the data-starved limit. And whether you actually exceed the CNN performance or merely get close to it, I, for one, am somewhat reassured by a really simple approach that seems to be really robust to contamination in the training data and robust under small amounts of training data, and that is generating coefficients that we can kind of assign physical meaning to, in the sense that we can rearrange combinations of them to be sort of maximally insensitive to rotation or maximally sensitive if we want to be. There are plots I didn't show you where we say not only identify the mnist digit, but tell me the angle, with which you can say what the original alignment should be. And our floor on that gets down to, at least for digits like 1, gets down to the intrinsic noise and the alignment of the digits in the data set. So we can choose to get rid of sensitivity to orientation or maximize sensitivity to orientation by trivial rearrangements of the outputs of this. And that's just one example. So we're working on doing this in 3 dimensions, either the fully spherical version or the 2+1 dimensional version, where you do exactly what I just showed in 2 dimensions, and then you kind of have an e to the ikz in the 3rd dimension. And that's useful for a lot of things. In astronomy, there are a lot of data sets where you have a position, and a velocity. The 3rd dimension is fundamentally different. Or a redshift survey for cosmology, where you have redshift space distortions that are affecting the 3rd dimension. So there may be a lot of cases where you want to do 3D inputs, but treat one dimension differently than the other 2. So anyway, we're exploring a lot of things like that right now, actually with a number of people who I see on the Zoom screen right now. But I wanted to just tell people about this a little more broadly, because I think this kind of an idea could be powerful, and it's quite straightforward to implement and easy to understand and executes fast and all that good stuff. So it's a nice tool to have in the toolbox. So I'll stop there. Thanks.
All right. Thank you, Doug, for the beautiful talk. That was great. I'm sure there are many questions for you. Are there questions coming from the audience? I see lots of claps, but I'm sure I'll see hands in a minute. Let me start. So Seb asked a question in the chat, so I'll start with Seb. Where are you? There you are.
Hi. Thanks for a great talk. Yes, so you showed some numbers about some. Can you still see me? Oh, my screen has frozen.
Oh, we can hear you.
Oh, so okay, you can hear me. Good. I think I have a problem with the internet. So yes, so you showed some numbers when you were training some some models on non-rotated data and then testing on rotating, and your model was getting about 92% accuracy, which kind of makes sense to me. If you have 10 classes and 2 of these classes are hard to distinguish, the 6 and the 9 problem, then 92% makes a lot of sense. But some of the model were still getting 99% accuracy. And I was wondering, do you know why that is? I mean, somebody in the chat suggested that a handwritten 9 is not a flipped handwritten 6. Maybe that's the case, but I was still surprised by this 9% accuracy.
Yeah, no, I think a human probably could not tell the flipped 6 is not a 9 all the time. You can tell sometimes, right? Some people very clearly make their 9 like that, whereas the 6 is like that. A 6 is just a continuous loop, not a turn around and go back. But different people write things different ways. So, the mnist data set has a lot of diversity. And I was astonished how well those spherical neural nets can tell a 6 from a 9. I would not have thought that it could be done with that precision. So yeah, if you're willing to train millions of parameters or whatever instead of doing something very simple like this, you do get better performance on separating things like that.
Thank you.
Excellent. Thanks for the question, Seb. Jesse's next.
Great. Thanks, Doug, for the talk. So I want to make sure that I kind of understand the big picture here and kind of which of your 3-letter acronyms are the most important. So there's the WST part, which is in some sense, if I understand, a pre-processing that accomplishes the goals that you set out of having something that has at least this proximate rotation invariance and having all the kind of the energy conservation and such. And then that's the kind of pre-processing step. And then you have a post-processing where you happen to do something very simple of this linear discriminant analysis. And if I understand, the magic is more in the WST part, and LDA, you could have replaced that with something else. It could have been something even fancier. Do you have a sense if you were to kind of take the post-processing and swap it out for, like, for example, doing a neural net at that stage, let's say a fully connected network at that stage, whether you would still preserve the features that you would want for your science applications?
Yes, so that's literally on the to-do list. Bolt fully connected neural net on the end of this, because I would be interested to see how much we benefit from sort of explicit invariances built into the early stages, but then all the richness of the neural nets at the end. So we're just doing LDA at the moment because it's easy to understand. Or another thing Andrew's actually done is a linear regression on the WST space itself. Just do a regression. The problem is this stuff is not necessarily linear in that space. It's usually kind of quasi-linear, and so you usually don't do quite as well that way. You really want something kind of nonlinear on the end of it. So there's certainly more work to be done there.
Great, thanks.
But it is a good question where the magic is, because one of the other things we did, we wrote a paper a few years ago where we tried to make the three-point function, or really the Legendre projected three-point function of the form that Daniel Eisenstein and Zach Slepian were pioneering at the time, because that's something that's easy to compute quickly. We did not get a very good performance in separating those MHD simulations from each other using that approach. But then Andrew took that output and put it through LDA, and it did much better. So some of the magic here is just, what is the right dimension reduction for whatever thing you're feeding in? And some of the magic is let's start with something that has all the invariances we want, and then go from there.
Excellent. Thanks for the question, Jesse. Georgios.
Let me unmute. Great. Hi, Doug. Thanks for the great talk. That was very nice. So I was particularly interested about the plot you showed of the power in the coefficients as a function of angle, I think. So what I didn't get, though, was what separates or what determines whether you'll have a smooth curve or a noisy one. Is this a function of scale or something else?
Yeah, that's a very good question. This is the kind of thing that Andrew and I have extensive discussions on. If Zoom would cooperate, I can show that here.
I see something.
I feel like the computer's right on the edge of being overwhelmed. Okay. Yeah. So as I showed way up here somewhere, the filter bank, there were, yeah, well, I'll never find it. Oh, here.
Scales.
Right. So you can imagine you take some pattern, you rotate it in real space, and we've tried to apodize things in a circle so you don't have corners of the image rotating off the image, and make sure things are well sampled in the sense that there's not a lot of power out by the Nyquist frequency at the edge of the Fourier plane, right? So you want to do a little bit of preconditioning to make things a little bit nice, because if an image isn't well sampled, rotational invariance isn't well defined really. But that said, we have these things that are kind of pixelated in Fourier space or in real space, and it's going to be hard to get those exactly right. And so I think it's safe to say in general, a lot of these places where you see the oscillations are the coefficients, either on the biggest or the smallest scale, that just aren't, they just aren't quite right. And you can mitigate that somewhat. You're allowed to pad out your image, which stretches the Fourier transform, kind of bends it up to a bigger image, or you can stretch your original image to have it better sampled, and that pads out the Fourier transform to push Nyquist farther away. So by resampling and padding, you can put those nasty scales that don't work as well far away from where the information is. And so we've experimented with those tricks a little, and they do They do improve performance. Obviously, when you do that, it's going to cost a little extra computation, but this is something that's so fast, we have a lot of overhead for doing that. I mean, a lot of margin for making it slower.
Great. That makes sense. Thanks a lot. Great talk.
Excellent. Any other questions for Doug? Phil.
Hi. Yeah. Just a question. I'm wondering, for training your data sets where you don't have enough data to train, have you looked at approaches based on like one-shot or few-shot learning?
We haven't actually. We should actually get into that literature, because I know people have thought about that a lot. And so I want to make, I should be cautious about statements I make about neural networks, right? Because there are a huge number of varieties of approaches that people have tried to address exactly that problem. Niklas has a hand up.
All right, can you hear me?
Yep.
On slide 57, you have this amazing plot where you show with 50% bad data, right? You still have 90% accuracy. Do you have something similar for the other models that you compared to?
I would love to, actually, but unfortunately, we're not running these. We're just pulling numbers from their papers. Right. But I would be interested to see that, actually. Yeah. I do not have a good sense of how quickly the performance degrades as you mix garbage in with the training data. In subsets, all of these things are almost just a fitting function in a high dimension space, right? And you're just specifying fitting functions that are more rigid or less rigid. This is pretty rigid in the sense that there's not a lot of freedom. But a neural network that has a lot of capacity, may just try to memorize the bad training data. And of course, you regularize it in various ways, and you force it not to do that. But that's probably what it wants to do. Its inclination is to memorize the bad data and try to mimic it. And with something like this, it's just sort of not even possible because it's too rigid. It's too simple to do that.
Okay, right.
But yeah, what really matters is actual performance and actual applications. And so we're getting to those applications, and we're happy to have a bake-off with other approaches. I know people are applying neural networks in cosmology right now and getting pretty good results. And it would be fun to see, as a function of amount of training data, how things vary. I mean, I'm really not necessarily making the claim that we're going to beat the neural networks at the end of the day. The question is just like, how well can you do with something that's really simple?
Doug, if I may piggyback on that, because it's related to my question. I mean, a lot of times people, particularly when they're first getting into deep learning, sort of wring their hands about interpretability and sort of say it's all black box and you can't do anything. And I think one thing you're really advocating here is that if you can get good enough on the accuracy with simpler techniques, you might be able to interpret the results just by virtue of having a simpler technique and opening the hood and whatnot. Is there, in what you've done so far, is there anything sort of concrete that you can interpret about the interstellar medium that maybe was a surprise relative to what you knew before?
Not yet, because we've only taken baby steps to applying this to real data. I didn't show it, but I looked at hundreds of dust images after dinner one night and classified them into 6 classes, just according to, do they look diffuse or clumpy or cloudy or magnetic dominated or I don't know what, just some classes that need not have any real meaning. And then we did the WST LDA thing on that. Also tried UMAP and some other more sophisticated things. But it's fun how, you can just take those classes defined based on a small amount of training data and then sweep over the entire sky and say for each patch of sky, which class does it fall in? And then, see things pop out. So we're just beginning to play games like that. I don't have anything specific to say yet, but I am really hoping in the next several months that I do.
Excellent, thanks. I know in sort of the high energy theory community, this sort of thing can sometimes be really useful for uncovering decision variables that you can then like prove a theorem about, even if you're really lucky. And
yeah, that would be wonderful.
You couldn't do that with a black box neural network. Sorry, with a standard feed-forward network, it would be much harder than with these simpler techniques. And I think you're making a great point that simplicity can be a real advantage, and if it still is accurate. So.
Yeah, or at least one thing to have in the toolbox. I mean, if someone takes a bunch of cosmological, whatever simulations and compares the DESI data set in a few years, and does it with, Legendre projected 3-point function and a WST LDA and a neural network of various kinds and whatever. If you get the same answer from all of those, you're going to say, okay, great, I have confidence in this. But you'll probably get a slightly different answer from each one. And then we back up and say, okay, what are actually the assumptions going into all of these things? Right. So I think we just want to have multiple approaches and then see if we can find some, concordance.
Absolutely. Ning has a related comment in the chat. Maybe he wants to make the comment live.
Sure. Hi. I actually just joined this list recently. So I wanted to comment a little bit from the computer science perspective about what some of these interpretability results mean. So a lot of the interpretability results in the context of machine learning assume that you're learning about the data set, but you have zero priors about what the actual correct background stuff that you're trying to learn from the data set is. It's literally just a pile of dots that you're trying to fit a curve to, or you're trying to split into groups. But if you have, I think a lot of the potency of these arguments actually fall apart if you assume that you have some background independent information about the data set, such that you might not have been able to deduce at all a priori where the cuts were going to be or what curve you were going to fit to it. But after you see it, we can then do, I guess, what most people think of as doing physics and actually interpret why that particular fit made sense in hindsight. So I agree with Jim, I guess, in that I too am not too worried about some of these scary sounding non-interpretability results that some people claim.
Yeah, I think I agree with that. But it's good to have ways to explore, right? In the extreme limit where you have a model that you really believe, except for some fairly minor details, we believe our cosmological model is true. It predicts the power spectrum of the CMB brilliantly. It predicts all kinds of things, Big Bang nucleosynthesis works, there's just all these things that work that have been tested carefully and they work. And so when you have a model that you really believe and you're really trying to just pin down the parameters of the model with great precision, that's one limit. In another case, you look at all this dust and you say, I don't know, I just look at this, I can tell those clouds really look different from those clouds, but why? What is it about them that's different? Can you get me a list of all the things that look like that and all the things that look like that? And then maybe I'll see which ones I have some ancillary data that tells me something about them. I mean, I see it more as a tool to explore than the tool for the ultimate explanation or the ultimate, the best determination of whatever parameter.
There are some interesting questions from Glennis in the chat. Glennis, would you like to ask it live? I'll unmute you. I'm not seeing you actually on the participant list for some reason.
I see Glennis on the video.
There we go. She's there. I got to unmute her.
Now it worked. Doug, that was wonderful. I really love it. I just wanted you to, if you didn't mind, like delve in more detail to the physical example of where you trained on the MHD simulations, just to sort of explore a bit more what kind of physics and what kind of practical information you could ask for from your data, from your approach.
Yeah, so
like in 3D, you were doing 3D, or what were you doing? That confused me a little bit.
Oh, so the simulations are in 3D, and then we were just taking 2D slices of them. We also in that paper do projection.
So what kind of
the 3D box, right? We can do this in projection, and we also have a 3D version of this. But just for simplicity,
for example,
in the talk, yeah.
Right. But just for the, sorry, I have a satellite internet, so it's a miserable lag. But for example, what kind of, you mentioned Mach number, that you could get the average Mach number, but what kind of other things could you try to do just in the 2D, for instance? Because there's so many examples where we do have 2D knowledge. And yet the phenomenon is 3D. We're seeing it in projection, for example. I just wondered if you could just describe a little more in practice what you could pull out from a physical data set, as far as you know now. Obviously, you've only touched, you've only started.
Yeah. So one of the things Andrew is doing at the moment is looking at cloud factory simulations that are done by Rowan Smith in England. And so that's a simulation where they're putting a lot more physics into the interstellar medium. There are supernova explosions going off and shocks going through it and whatever. And, Andrew identified dozens of things parameters that you could try to get at. Now, of course, most of them we won't realistically be able to get at, but so it's not just necessarily the sort of micro things like what is the sound speed right there, what is the alpha Mach number right there, whatever, but how long since a supernova shock went through that. Recently shocked things probably look different than things that haven't been shocked for a million years. Actually, a million years is kind of recent, but you know what I mean. So things that are more about the larger environment might be things we can get at, in a photo dissociation region. The input from the radiation is really important. In a dark cloud, it's not. So I mean, we haven't thought too far down this path yet, because we've been more focused on the methodology to just see if we can recover some of the parameters that are knowable in the simulation, and then try to find the mapping between what we see and those parameters. Of course, that's in the context of somebody's model. That's in the context of the simulation. We don't know if that mapping changes a lot when you go to real life. So that's why we were also in parallel trying to do the thing of just take real data and try to separate that into categories, and then find other things that sort of look like that to me, and then see if that can go somewhere too. But at some point we have to bring these things together. We have to get simulations that are good enough that we really trust them to be able to calibrate data on the sky to physical parameters. And in cosmology, we can do that, or we can come very close to it because we believe our cosmological simulations are sophisticated enough. But that's really hard in the ISM. And so, yes, Glennis, there will be a lot of work here to find the right questions. Thanks, good to see you.
Well, maybe on that note, since there's been a lot of questions, let's thank Doug one more time. A lot of people have headed out. Doug, that was a wonderful talk, and you were also an exemplary citizen as far as ending 10 minutes early to make sure that there was ample time for questions. To have a solid 20 minutes of questions like that, I think really is part of the point of this series. And so it was wonderful. It was great to hear about your work. I'm pretty interested in it and need to look more into these wavelets myself. I haven't done much of that. So it was good to learn about a technique that's new to me. So thanks a lot, appreciate it. And this will be on YouTube and trimmed within 48 hours. So thanks.
Great. Yeah. Thanks a lot. And thanks to Andrew, who's in the room here. Andrew made basically all of the plots I just showed.
Thank you, Andrew.